Hello, everyone. Hello, Professor Koji Nakatogawa. Nice to see you. Hello, Dana.
Good evening, good morning.
Good evening. Yes. Hello, Yan King. Hello, Jake.
Hello, hi.
All right. Professor Koji, thank you so much for letting us use your professional account for this program. Thank you so
No
much.
problem. My pleasure.
Thank you.
Never mind.
You definitely need more than 40-minute sessions for your 2-hour lectures.
That's true. Yeah. I am still trying to gather some fund to be able to fund this in the future.
That's very noble.
Yeah, I really hope to be able to promote more of this mathematical logic to Southeast Asian public and also the world.
I'm sure there is a lot of potential.
Yeah,
somebody has to do it. So
that's true. Yeah, I'll need to do a little bit more, pushing with the local universities and everything to promote the subject.
It can be hard, and sometimes it seems it's good to try more than fewer. Like sometimes you run into not as much cooperation.
Yeah, that's true. It's been quite a challenge, to be honest.
Yeah.
Yeah, but well, I'll keep trying.
Well, you have support. You gathered international support.
That's true. Yes. So good. Yeah. So it's time. So without further ado, I will pass it on to Dana for the last lecture of set theory and also of the program. But before that, I really want to thank everyone for attending this program, and I hope you have get a lot of knowledge and inspiration out of this. Do hope to see all of you in the future as well. And so please go ahead, Dana. It's all yours now.
Thank you. I think that you need to make me a co-host on my iPad for sharing.
Yeah, I will give you the sharing ability.
Now yes, you can there we go. Thank you. Yeah, I'm sad that I wasn't able to go to all the other talks as well. Oh, this didn't work out. Once more. Share content here. Hopefully this time around. No, this here. Okay, you're there. And I didn't realize this was the last lecture. So applause to you who are here in person in early morning hours or late night hours. And I hope that this continues and that maybe we can even join forces. I think this would be actually very useful for our students as well. So we'll see what we can do in the future.
That's true. Yes. Hope we can do something together. Yeah.
There is something about this intensity. It is intense, but at the same time, it's you really get into things. So I'm glad myself that I'm doing it, although I'm very tired.
Thank you so much.
I signed up for it when I thought this would be my calm semester, but I should just stop thinking that ever is going to happen. So today I wanted to mention some open problems because that's where we should get, right? What is current? They're actually somewhat old open problems, but that makes them more substantial. And we are going to stay within the topic that we talked about. So there will be ultrafilters and there will be Checkstone compactification of natural numbers. So it's in the vein of set theoretic topology. But we are going to start larger, so than just natural numbers. So let's start with an arbitrary cardinal. Now to make the analogy, when we were looking at beta of n, then I'm thinking of this having the cardinality aleph naught, and it doesn't matter which set I choose, as long as the cardinality is the same, I'm going to get the same or isomorphic space of ultrafilters. So for any cardinal, I can look at the space of all ultrafilters on the underlying set of the cardinal, and look at the non-principal ultrafilters, K star. And when we look at non-principal ultrafilters, then finite sets do not matter, right? If I have a finite set in an ultrafilter, then immediately this ultrafilter is going to be principal, right? Because when I look at the partition of this set, one of the pieces has to be in there, so I can refine until I'm left just with one element. So that's where this ordering comes from. So often when we are talking about the subsets in natural numbers, from the set theoretic point of view, we are not really worrying about sticking out by a finite piece. So we say that A is almost contained in B if and only if A sticks out of B just a little bit. So I'm sorry, this is what I wanted to say, right? So A is not maybe quite contained inside, but it's almost contained inside. So what is going to stick out is going to be just finite. And we can also look when this holds in both directions, and then we get an equivalence relation. So we can look at when A is almost included in B and B is almost included in A. When we have just one direction, then of course B can be a lot larger. The difference between B and A can be large. So this is indeed important that we mention both directions. And I wrote down other ways what that means. Well, they're almost equal if they're almost equal, meaning that one sticks out from the other by at most finite piece. That means that the symmetric difference is finite, right? This is the operation of symmetric difference, which is the things that stick out. And another way to describe that is what is in both of the sets without the intersection is finite, right? So what sticks out is finite. Okay, as I said, the almost equality is an equivalence relation, and the almost inclusion is a partial order. That's very easy to see. And as always, if there is any questions, just jump in right away. So now, if I am in the non-principal ultrafilters, right, then looking at neighborhoods that correspond to almost equal sets actually give me exactly equal sets, right? So if I have A bar, which is all the ultrafilters that contain A, and I have a set that is almost equal to A, then actually the non-principal ultrafilters that contain A and B are the same, right? Because if it did happen that there was an ultrafilter that contained A, that was non-principal, but it did not contain B, then it would have to contain A minus B, and that would be finite, so it would be principal, right? So, and it actually holds also for the almost inclusion, right? If I have A almost included in B, then well, smaller set gives me bigger restrictions, so that would mean that the set B, where I'm looking at the larger set being contained, this is going to be a subset of the A bar. Okay. So modulo finite sets is fine when we scratch out principal ultrafilters, and this is the relation we will be looking at. So Katowice problem has an interesting story. Apparently it's a question that was asked about in Katowice, it's a city in Poland, during a seminar. And it was one of those questions where you think that something is obvious. That means in this case, something obviously cannot hold, but you just ask, okay, so how do you prove this simple fact? And that question was, whether the non-principal ultrafilters on one cardinal can correspond to non-principal ultrafilters on the other cardinal. So in this case, correspondence means homeomorphism, right? So is there a one-to-one map between some K star and some lambda star for K, kappa, and lambda different? Well, obviously, if we leave in the principal ultrafilters, right, this is not possible because these are isolated points. So if I want to have a homeomorphism, then isolated points, right, points of discreteness, they have to go to isolated points, right? So then I would have to have a bijection between kappa and lambda, and that exactly tells me that the cardinals are the same. So, but however, if you take away the principal ultrafilters, something very strange happens, and that is that this answer is not so obvious. So it turns out that most of the time the answer is still no. So that's a relief, but there is one unresolved case. And surprisingly, this is the one that you would think would be decided the first. And that is whether omega star is homeomorphic to omega 1 star. So I'm going to use omega and omega 1 because this is the usual way that this is spoken about. Of course, this would be the same thing in saying n star here. Or when we were talking about cardinal numbers, this should really be aleph naught star. And this should be aleph 1 star, right? Because we have the alephs for the cardinal numbers and omegas for the ordinal numbers. But as you know, sometimes things just catch on in a little irregular way, especially around the countable versus uncountable. So it's habitual to say omega instead of aleph naught in this case, and omega 1. But with respect to cardinals, it would be aleph naught, aleph 1. So the only place where this is not clear still after about 40 years is between aleph naught and aleph 1. Is it possible that ultrafilters and natural numbers, non-principal ones, are indistinguishable from ultrafilters on omega 1? So that seems absolutely ridiculous, right? It seems like there is no way that these two spaces could be homeomorphic. There is so much difference between omega and omega 1, but nobody has been able to prove it. So any model that anybody has looked at with respect to this question, and this question has been worked on a lot, exactly because of how foundational it is, there no such homeomorphism exists. So any model that people studied as for and looked into what these spaces look like give us consistently a negative answer, but we don't have proof in ZFC that such a homeomorphism cannot exist. So it led to a lot of development in forcing and trying to build new models where, let's say, consequences of such a homeomorphism would be impossible, proving that such a homeomorphism doesn't exist. There was a lot of beautiful work done there. So, for instance, we know that we know the cardinalities of these spaces, right? We talked about Pospíšil's theorem that told us that whenever I start with a set of certain cardinality, then the space of all ultrafilters under AC is 2 to 2 to that cardinality, right? So here, if there is any chance for the homeomorphism exist, then 2 to 2 to aleph naught have to be equal to 2 to 2 to aleph 1. But this is not impossible. This holds in many models. So this is not going to resolve it. Any questions? Okay, so this is the part where I'm going to present some proofs because they are short enough to reasonably present them on slides. So we are going to make a reduction, right? We want to show that this is really just the last case that is out there. And that can be done however, it is not obvious. You have to prove it. So the first lemma in that direction is that if I do have a pair of cardinals for which there is a homeomorphism, then they are also going to be homeomorphic to star of any of intermediate cardinals. So I am going to choose a minimal failure, so minimal counterexample to this lemma for the sake of contradiction. Now, maybe let me ask if everybody is familiar with the lexicographic ordering. It's sometimes also called the dictionary ordering. So you can imagine, right? In the dictionary, you first have everything that starts with A. Sorry, maybe not. There are different alphabets. So if I take the Latin alphabet, then that would be the case. Everything that starts with A, everything that has after also A, and then only after the ones that have B, and so on, right? So this is the same thing. So we are looking at the first coordinate, and if that coordinate, if I have two pairs and I have something greater in that coordinate, then it's immediately going to be a bigger triple no matter what happens after, and then I just go coordinate after coordinate, okay? So I'm going to take the smallest counterexample and reach a contradiction by finding obviously a smaller example. So let's suppose that the smallest and the largest cardinal, Q, K, kappa, and mu give me a homeomorphism. And I'm going to look at this lambda. So because lambda is smaller or equal than mu, then it is a member of mu. I mean, otherwise, if it was equal, there is nothing to prove. And so because it is an element, it's a subset as well, right? Cardinal numbers, they are transitive. So I am now thinking about lambda as being an initial segment of mu, right? And mu continues somewhere. Well, that means that lambda star, that is what would correspond to the lambda bar, right? If I think of it as a subset, has to have an image. And because I have a homeomorphism, then the image also has to be a clopin subset of K star. So it's going to be some A star. Okay, so now I am looking at failure, right? That means that I'm claiming or hoping that I can find such a triple where a lambda star is not homeomorphic to kappa star. And then that means that, well, lambda star is homeomorphic to A star. So this A has to be of cardinality smaller than kappa, right? Because otherwise I would have a contradiction with minimality of my triple. Okay, but well, then I still have a contradiction, right? Because if I don't get the contradiction in one of the coordinates, which would be lambda here, then I get a contradiction in the first coordinate. So I would have that this new kappa lambda is also going to be a counterexample, and it would be a smaller triple. Okay, so very standard trick that if you have a counterexample and if you can, you want to use well order to find something smaller. Okay, so this was the first reduction, and that means that if I have two cardinals, then anything in between is going to also satisfy having a homeomorphism. That means in particular, what is in between two cardinals? Well, successor of the smaller one. So let's recall, this is something that you have learned in the first two lectures, that every cardinal has a successor, right? It never stops. I always have a cardinal that is larger than the previous cardinal. And there is a minimal such because cardinals are well ordered, and this is the notation. So now the claim is that actually whenever I have any two kappa star or lambda star homeomorphic, then I can show that they will be homeomorphic to omega star, right? So this is the same as saying that if kappa star and kappa plus star are homeomorphic by the previous lemma, and we will use it here again by choosing smallest such, right? So suppose that I have something smaller than kappa and I have lambda star and kappa star homeomorphic, well then I will have lambda plus in between, okay? Unless I already have kappa. And therefore I can just take the smaller one, and by the previous lemma, lambda plus star also has to be homeomorphic to lambda. So without loss of generality, we could also think that kappa is minimal. So let's call it lambda, and we fix a homeomorphism between the two. And now I'm going to show that I can actually deduce out of that a homeomorphism with omega star. Okay, so how do we do that? A little bit of cardinal arithmetics. So now if I take any alpha that is in lambda, right? Lambda is the first ordinal of cardinality lambda, right? So every element of it, meant as a subset of it, is going to have cardinality strictly smaller than lambda. Okay? This is how we define cardinal numbers to be the ordinal that is the smallest of that cardinality. So now for these subsets of cardinality smaller than lambda, I'm going to find their matches, right? So H needs to map the Klopen set corresponding to alpha somewhere in lambda plus star, and it's going to, these sets are going to be denoted by A alpha. Okay, well, now because lambda was minimal, counterexample, and alpha, cardinality of alpha is less than lambda, and I have this, this homeomorphism in here, then I also get that A alphas have to have cardinality smaller than lambda, otherwise I would be able to go to cardinality of that alpha and I would have a smaller cardinality. So now I have lambda many lambda many sets of cardinality lambda, and therefore I cannot reach lambda plus, right? Because I will have only a set of cardinality lambda that I am taking away, and therefore what I have left is lambda plus, and this should be plus, of course. Okay, so I'm taking away, but in a way, almost everything on the lambda side, right? Because I'm looking at the, on the lambda side, I'm taking away almost everything, and on the lambda plus side, very far from that. So this is going to give rise to our countable set in the middle, right? So now I'm going to look at a B that is a subset of lambda, such that B star is going to map on this set, right? Again, that has to happen. I have A star in here, so the preimage of that is going to correspond to some Klopen basic set that is given by some subset of lambda. But now, if you see that we were taking away all these images of elements of lambda that go all the way to lambda, that means that this B cannot have almost anything in common with any of the alphas on the way, right? That means that they are, the stars have to be disjoint, which means, as we said at the very beginning, that the intersection has to be finite. B can only eat out finitely many things out of A alpha so that it looks like it has nothing in common. But then, because lambda is the union of all alphas, such that alpha is in lambda, I get that this B has to be the union of intersections on the image side. So and each of these is only a finite set. So I have an increasing union of finite sets, and that cannot be more than countable. So I get that I have this countable set that is actually, whose star is homeomorphic to A star for A of cardinality lambda plus. Okay? So that seems very ridiculous, right? That if I start with some very large cardinal, then I would be able to go all the way to omega star, and already how the proof goes sort of shows like this shouldn't be possible at all. So it turns out that indeed you cannot have any large cardinal be in that position. The only one is going to be the one that's only one apart as for cardinals. It cannot be anything larger than that, right? Because if I do have something larger, then I would have, right? If I have omega star homeomorphic to, sorry, if I have some kappa and lambda, kappa star homeomorphic to lambda star, well, then I know that all of these are also homeomorphic to omega star, right? So whatever the maximum of kappa lambda was, anything in between is going to be homeomorphic. So this would be homeomorphic to omega 1 star and up to the maximum of these, right? So in particular, if one of the kappa lambda was at least omega 2 star, I would get that omega 2 star is homeomorphic to omega 1 star, and this is not possible. So that will show that the Katowice problem, as we stated it on the first slide, is the last instance that keeps unresolved. So I'm not going to give a complete proof of this, but I'm going to give an idea of what goes into it, because that's also a very natural and common concept in set theory, set theoretic topology, and the small cardinals, the ones between Aleph naught and continuum. Okay, so the point is that if there is a homeomorphism with omega star and some other cardinal star, then the space of functions omega to omega would have these cardinality sized scales. So I'm going to say what these are, but I'm going to first say how we think about these functions. So these are just functions from omega to omega, the bare space as we always know it, although I'm not sure how much has been told about it in the first two lectures. But we are going to equip that with a partial order. And this is a partial order that makes it so theoretically very interesting. And it's going to be, again, the star order. That means that we do not care about finite piece, but from some point on, I'm going to have a true comparison, right? So F less or equal star G is that F is almost everywhere below G. That is for all but finitely many n's, Fn is truly less or equal than Gn. And of course, I can then define that F is almost equal to G if both directions, and as you see, very similar to sets as in the beginning, it's just a variation, right? And it also then means that they are the same except for a finite set. And it's again easy to verify that the less or equal star is a partial order and that equality star is an equivalence relation. So now what is a scale? A scale is a sequence of functions that is well ordered by this order, and it is dominating in this order. What does it mean, dominating? It is the same thing as saying cofinal. That means that for every G among these functions, there exists some alpha such that G is bounded by this F alpha. Okay, and this order gives a rise to many cardinal invariants, many cardinalities that are uncountable, and less or equal than continuum, and they have many applications in models where the continuum hypothesis doesn't hold, and we actually do have space for different cardinalities. And you can say, for instance, the dominating number would be the smallest set functions that give me a dominating family. How many functions do I need to dominate this order? So here I also want a well order, which of course I wouldn't be able to get an uncountable sequence if I was requiring a true inequality, right? So the star makes this a lot more interesting. Okay, so basically to finish the proof, there is this lemma that we will prove and theorem that would be a little more lengthy, which says that there is at most one regular cardinal kappa such that a kappa scale exists in omega to omega, and omega 1 and omega 2, they are regular cardinals, so that works. And if there is some uncountable cardinal for which kappa star would be homeomorphic to omega star, then such a scale would exist, right? So the scale doesn't need to exist at all, but if I did have a model where the homeomorphism exists, then I would also get a scale. Any questions? Have you seen this order before? Well, okay, I hope you will once again. Okay, so let's see. So we are going to show that we cannot have two scales. That means we cannot have two sequences that would be scales and they would have distinct cardinalities, regular cardinalities. Let me maybe recall what a regular cardinal is, right? So kappa is regular if the cofinality of kappa is equal to kappa. That just means that I cannot climb my cardinal in a sequence of length smaller than kappa, right? The cofinality we had on a previous page. Let me maybe give you an example of a cardinal that would not satisfy that, right? Because we have, well, usually we look at uncountable cardinals. So Aleph1, Aleph2, these would all be regular, but then there is their limit, and this is Aleph omega, and this is not regular, right? Because actually the sequence Aleph1, Aleph2, and so on is cofinal, so it has cardinality omega. So there are uncountable cardinals who have countable cofinality, or anything smaller than itself is possible. These are called singular cardinals. I think actually you spoke quite a bit about singular cardinals. So these are the regular ones, and they have typically nicer behavior, right? Because then you can do cardinal magic by not being able to climb up in too few steps. Okay, so this is for regular. Now, suppose for the sake of contradiction that I do have two scales of different cardinalities, and I'm going to say that kappa is going to be smaller than lambda. And I'm also, just to make it easier, assume that they are already enumerated in the well order with this order less or equal then, right? And my assumption is that this is a well order. So now I'm going to dominate one by the other because these are scales, but I'm also going to make sure that when I'm making the choices where G's dominate F's, I'm not going to choose a G that is actually almost equal to F. So that's why I'm going to take this additional step and I'm going to intertwine these with these H alphas. So whenever I have any F alpha, then I'm going to just shift it up by 1. Then now if I am going to find some G that almost dominated, well, it can be below H, but then it has to be at least at the level of H or above. It could actually be H, but it definitely, this +1 will make sure that therefore it has to be strictly above F. So when I am now going to be choosing these witnesses, B alpha, that say that the elements of the G alphas, they dominate the F alphas, I'm going to choose them so that they actually show the dominance of the H alphas. They dominate a whole family omega to omega, so I can make that choice. So I'm going to make this choice. And by shifting these F alphas to H alphas by 1, this is going to tell me that F alpha cannot be almost equal to G beta alpha. Okay, now I use regularity magic, and that is that now because kappa was smaller than lambda, then there is no way that I can take just kappa many elements and reach everything, right? So that sequence of the G beta alphas cannot be cofinal in that order of G alpha. So there has to be some nu that's above all of the beta alphas for alpha in kappa. And then obviously we have that therefore, but well, this I didn't actually write it, but I have that G, I write it. Well, I guess it's down there, but make it explicit here. G beta alpha is less or equal star than G mu, because we have them enumerated in an increasing order. So now this G mu, however, has to be dominated by something from the F alphas. So let's have that alpha from kappa that is going to dominate. So now I have that, well, F alpha dominates G mu, but also F alpha is dominated by one of the G beta alphas, and that has to be dominated by G mu. So the only way to make that happen is if F alpha was almost equal to these G's, in particular, the G beta alpha, but we chose the G beta alpha so that almost equality was not possible. So, again, simple, typical way of argument. Okay, so now we have shown that the Katowice problem only remains unresolved for omega and omega 1. And there has been many attempts to solve this, as I said, a lot of them involving forcing, showing consequences of existence of such a homeomorphism and trying to prove that these are absurd. And it just has produced a lot of very interesting results. So maybe it's a blessing that we do not know the solution, because it is just the source of many interesting problems and results. So one approach is more dynamical, which is closer to me in nature. So this is something I'm going to tell you about a little bit. And that is trying to distinguish them, not directly, but by looking at their homeomorphism groups, looking at all homeomorphisms of n star and, well, okay, I'm sorry, I have written these slides on different days. So this is omega star. This is the same as omega star. So let me just talk about n here. So of course, when I have any permutation, then this permutation lifts to star, right? Let me just recall this lifting property. Well, beta n has this property that if I have any function from natural numbers into a compact space, which beta n is, then I can always extend this function to all of beta n, right? So this is going to be my beta f, beta phi, and then the phi star is going to be the restriction. So this is just beta phi star, sorry, beta phi restricted to n star. Okay, so obviously if I start with a permutation, then I end up with a homeomorphism. However, I can, again, forget finitely many points on the base set if I am only looking at non-principal ultrafilters. So I can actually also obtain homeomorphisms by forgetting finitely many elements on either set and have a bijection between these two. So the most basic example would be just a shift, right? I have natural numbers 0, 1, 2, and so on, and I'm going to shift them by 1. So 0 is going to be mapped to 1, 1 to 2, 3, and so on. So the image is not quite natural numbers. It's natural numbers without 0. So it is not exactly a permutation of natural numbers, but it's an almost permutation modulo finite. But then again, in n star, this is not going to make any difference, and I'm going to get homeomorphisms. And such homeomorphisms are called trivial because they come from a point map on the base set. Okay, and it turns out that how homeomorphisms are, or how many even there are, is independent of ZFC. So under CH, this is an old result, one can show that there is as many as one could possibly hope for. So there's 2 to the continuum many homeomorphisms of n star. But a lot more surprising result came with Schillach, who showed under proper forcing axiom, so one of the nowadays standard techniques, but with striking results at its beginnings, that the only homeomorphisms of n star are actually the trivial ones. So PFA kills anything that is non-trivial. So that's quite striking that there is such a huge disconnect in what can happen under these wildly accepted reasonable axioms. And Velichkovit proved that you do not need the whole force of PFA, you just need open coloring axiom. So that's a Ramsey theoretic statement that has been used for many more results of this type. Okay, so let me just mention one result that connects these two things. So it connects the Katowice problem with the group of homeomorphisms. And the proof is actually very nice, but still it's a couple of pages and will take the rest of the lecture to show. So it shows that if we do have a model where there is a homeomorphism between omega star and omega 1 star, then there must exist a non-trivial homeomorphism of omega star. So such a model cannot come anywhere close to PFA. And how this is built, it's actually very simple, but I'm presenting it here to get an idea of how we can use the fact that it doesn't matter what sets we are choosing for our star, it only depends on what the cardinality is. So instead of omega, we choose here z plus omega. So integers, sorry, not plus, times omega. So we have the grid, right? So we have, well, I guess it's the other way around if we want to follow calculus style, right? So I have z here, and on each z I have omega. And the other one is just going to have the vertical lines, omega 1, but because these are the same cardinalities, then the stars have to be the same. So if I have a homeomorphism between omega star and omega 1 star, I have to have one from S1 star to S0 star. And how do I get the non-trivial homeomorphism is that I am going to look at my z in this direction, right? And I have my aleph 1 here, omega 1 in this direction. And I'm just going to look at the shift in the z direction. So the sigma that we had before, but here on z, so this is an actual bijection, I'm going to just move everything to the right by 1. So this, of course, gives rise to an autohomeomorphism of this space S1 star because I have a true bijection on the base set, and then I can compose that with my homeomorphism H. So I can go from S0 star by H inverse to S1 star, and then I can go inside of S1 star by sigma star, and then I can go by H again back to sigma star. So this is sigma 0 star autohomeomorphism, and KP Hart was able to prove that this is non-trivial. The methods are absolutely elementary, and it's quite recent. Well, I guess time flies, but definitely within last 5 years, I would say. So it's a newer idea to connect with dynamics. Any questions? Okay, so let me mention this problem that is, again, one of the classics, and somehow it just seems like it needs fresh ideas from young people. So I think that one should not build their thesis around problems that have been open for 50 years, but it's never a bad idea to be aware of them. So this is, again, set theoretic topology related to beta omega. And it is a question whether if you have any compact space, does this space need to contain a convergent sequence or a copy of beta omega? So these are somewhat two extreme opposites, because beta omega does not have any non-trivial convergent sequence. So let's just recall that if you have a compact space that is metrizable, then every sequence has a convergent subsequence, right? So it's sequentially compact. But if you go into larger spaces, non-metrizable spaces, then this need not be true. And we talked about beta omega not being metrizable. 2 to kappa for any uncountable kappa is a non-metrizable compact space. So it's easy to come up with non-metrizable compact time in a very natural way. And this has been answered partially in the 70s. Fedorchuk gave a few examples under different axioms that are consistent with ZFC. But so far, there is still no ZFC example that would show that you can find a space that does not contain neither convergent sequence nor a copy of beta omega. So that is often, I would say, any paper that speaks about open problems in set theoretic topology is going to have both Katowice problem and Efimov's problem. But I think that there has been a lot more success with partial results for Katowice problem than for Efimov's problem. Okay, so now I see that I didn't include proof. So let's see how would such a proof look like. So suppose that I would have ultrafilters U1, U2, and so on in beta n that actually do converge to some U. Then that means that for every neighborhood of U, there has to be all but finitely many of these UIs that are in this neighborhood A. But then I can split the AI into two pieces such that both of them are going to have infinitely many of these UIs. So these are infinite sets. And this ultrafilter U has to choose one of them. So that's a contradiction. So this basically says that when I look at an ultrafilter, it cannot be generated by countably many sets. You need to, every ultrafilter base is uncountable. So many spaces do contain a copy of beta omega. There's, of course, that means that there is a discrete subspace of size omega, but that is almost always true. So it's just hard to think of a space without any additional axioms. I know there is another space under diamond, which is a consequence of CH, but it is weaker, but not much progress, I believe. Okay, so now I would like to switch gears. So if there are any, not exactly, but go to another problem. Okay, so this is something that I advertised in my last lecture, and that is to distinguish between dimensions. So it turns out that if I look at n squared as my base set, the grid n squared, and I take ultrafilters on that, then this is actually very far from looking at ultrafilters in pairs of ultrafilters in dimension 1. So first thing to observe is that they cannot be the same because one of them is extremely disconnected and the other one is not. So this is a property that metrizable spaces cannot have unless they are finite. So again, we are looking at large compact spaces. Nevertheless, in set theoretic topology, they naturally appear, such as beta x for any discrete space. So all the spaces that we have talked about are extremely disconnected. So what does it mean to be extremely disconnected? It's disconnected, but even more than that, if I take any open set and I'll take its closure, this is going to be open. And of course, if I have a closed closure of a set, this is closed. So in other words, every open set has a closure that is a clopen set. Right? So it's very, very disconnected, meaning that it has a lot of clopen sets. So now, if I do have beta x, why is that extremely disconnected? Any thought what it means there? Well, we just go with the definition, right? We take an open subset O of beta x. Well, how does that look like? This has to be union of elements of a basis, and we can choose the clopen basis of my A alpha bars for some A alpha subset of x. Right? This is a basis. This is how we introduce the topology on beta x to start with. So now, what is O closure? Well, the closure is actually going to be the same thing as looking at all ultrafilters that contain the union. And this is, of course, not taking all A alphas, all subsets of X, but just some for some alpha in some index set I. Right, and we definitely have in subsets of X, we do have unions of subsets of themselves. So this works out fine. I think in the end, I'll try to talk a little bit about stone duality between compact Hausdorff spaces that are zero-dimensional and Boolean algebra. So in that language, this would mean that the clopen algebra is completed. It has arbitrary joins and arbitrary meets. So here the join of these clopen sets would be take the union and look at the set corresponding to that. Okay, so without further overdue, the product is actually never extremely disconnected. So whatever you start with, the product is not going to be extremely disconnected. Well, this only makes sense if you start with extremely disconnected spaces, because you can think that X and Y are subspaces of that, so they have to be extremely disconnected. And let me just draw a proof of this, right? So if I have something extremely disconnected, then that means that open set has a closure that's open. Well, how do open sets look like? We have the product topology, right? So we have that that every open set is going to be a union of products of open sets from both sides. So what we are going to do, we are going to take in X, we're going to take a sequence A alpha for alpha, okay, well, unless finite, right? So if one of them is finite, then of course this would work. So I'm going to assume that they are not finite. So I'm going to take infinitely many Clopen subsets in each that are disjoint. So A alpha Clopen, this is what I get just from disconnectedness, and they are going to be pairwise disjoint. And the same thing for Y, I can take these. And then I'm going to take for my open set, for which I will find out that the closure cannot be open. I'm just going to take product of these, right? So I have partition on each side. Okay. And now if these are going to be, this is going to be, the closure of it can be also open, then by compactness, it has to be covered by finitely many of products of Clopens like that. So there would have to be some finitely many things that are going to cover this. Those do not need to be disjoint by any means. They also do not need to really cover full pieces, but altogether we cover by only finitely many. So now finite versus infinite tells me that there will have to be some of these orange squares that is intersected by at least two of the purple squares, right? So for instance here, but then just checking what that would mean. Well, then that means that I have intersection on the projection on the X coordinate, right? Between the orange and the purple here. And then also in this direction, I have this and that. And then, well, that tells me that, however, I also need to have that this square, because I have exact equality between the products of the infinite families and this finite family, that this would also have to be in my original set that came from these A alpha, B alpha. But this is not possible, right? So if I had anything that would be a join of these, then it would have to contain things that it doesn't contain. So this is a property that doesn't go well with products, but it, however, makes it a lot more interesting. And there has been a little bit of work. I'm actually surprised that there hasn't been a lot more in trying to distinguish these. It's true that there is still so much work left in one dimension that maybe that's the reason. And the second dimension is used sometimes. And sometimes there is these products of ultrafilters, but there is only a few papers that are, however, are interesting. And my personal interest there is in dynamics of discrete groups, and in particular, the relationship between dynamics of natural numbers and their square. So it just popped up naturally. Okay, so, well, we can definitely connect these two spaces, and obviously this one, this one is the larger one, right? Because if I have any ultrafilter on, any pair of ultrafilters in beta n, right? If I have any UV, then I can look at products A cross B, where A is in U and B is in V. And this is going to generate some filter, right? So I can close upwards, and well, I guess it's closed already under intersections. I can close upwards, and this gives me a filter, but this is not going to be an ultrafilter unless I'm looking at principal ones. So there is going to be many ultrafilters that extend that or not. And we will see that there are interesting possibilities. Most of the time there is going to be many, but there could be even just finitely many under some set theory conditions. So how do we compare them? It's exactly by looking at such preimages. So what do? We just look at n cross n, and we look at the projections into both of the coordinates. I can think that this is the first coordinate, this is the second coordinate, and then I can look at the beta extension, right? So when I have these, oh, I forgot. And to the nth projection, right, and that gives me a map from beta n cross n to beta n, right? So it gives me one lift. So this would be part of the pi that goes here, and then the other projection gives me the other lift. So it's really just pairwise. It's not anything intertwined. And that also means that this map is really easy to describe, although we don't understand exactly how it works. But if I have an ultrafilter, I'm just going to look at its sets and project these sets onto these coordinates. But of course, many subsets of n squared are going to have the same projections, right? So that's what makes this interesting in the end. So this is the map we are looking at, and now we can ask how large the preimages are. That means if I start with a pair of ultrafilters, I look at the filter generated by products of their element. How many ultrafilters are going to extend that? And it turns out that it can never be one-to-one, right? So I think the first thought, naive thought, would be that these spaces are just the same. So that falls through very quickly. And that is that whenever I have any two non-principal ultrafilters, then the preimage is going to have at least 2 points or 3 points if U and V are the same. And this is just by knowing that every ultrafilter is going to have to choose out of these sets. So I have a partition of n cross n into the diagonal, and everything that is below the diagonal and everything that is above the diagonal. And now if I have these ultrafilters UV being non-principal means that all of their sets are infinite. So if they are different, what can happen is that there will be some, part that they are going to miss the diagonal, but they will have to intersect both of these sets, right? And then of course, I can then extend by either of them. And then if the ultrafilters are the same, then I also have to intersect the diagonal, right? So then I get at least 3 preimages. Okay, well, that was simple. However, nothing else is that simple. So I'm going to give you more of an overview of the funny things that can happen. And I can give you a reference to where you can find those. So Hindman, this is the Hindman from Hindman's theorem that we talked about last time. He showed that if you find these, if you look at ultrafilters that are in some minimal left ideal, so this is going back to viewing data n with the addition extended from natural numbers, making it into a semigroup, then we showed that there has to be some minimal left ideals, right? And if I take two elements from there, then under this map pi, there is going to be many preimages. So definitely there are some ultrafilters that are going to have infinitely and actually uncountably many preimages. And another type of ultrafilters that appear in minimal left ideals, but they don't have to be for a minimal one, are the idempotent ultrafilters, right? These were the ultrafilters where V plus V was equal to V. And this was proved by Blas, Andreas Blas, with similar method as Hindman's theorem. So basically building the sets that are going to be extending these images by understanding how what sets are included in idempotent ultrafilters. And then I thought it was neat to connect this back to p-points that we were talking about in the first lecture. And let's recall what p-points are. So we know that p-points do not need to exist, right? That there are models of set theory in particular. Okay, I'm sorry, I'm not sure now. I think under PFA, you don't have p-points. So they don't need to exist, but they can exist, right? Under CH, you can construct them. So p-point was a point where if you had any countable sequence of open neighborhoods in N star, then below that countable family, there was always even a smaller neighborhood, right? In other words, if I have a countable family of sets, then there is going to be a pseudo intersection, an element of the ultrafilter that is almost included in each of these members of the family. And there is an equivalent characterization, which is in terms of functions, which is more suitable for combinatorial methods. Right? So the neighborhood that's more topological, if you want to think about it more pointwise, more combinatorially, then the function definition is more suitable. So what does that say? It says that whenever you have a function from omega to omega, then this function is either going to be constant on a set in the ultrafilter, or it is going to be finite to 1. And so I can also think about it in terms of partitions, right? For each element I in here, I can look at all the elements that are curled by I, and that's going to be a set pi. And because I'm looking at a function, these has to be disjoint, right? So I'm looking at partitions, but of course these can be not into intervals as it looks like, but into infinite sets. And now either one of these pieces is in the ultrafilter, or there is a set from the ultrafilter that is going to intersect each of these pieces of the partition in just a finite set, or even empty set, right? But at most a finite set. Okay, so how do we see that these two notions or these two definitions that we are claiming the same are indeed the same? Any thoughts? Any thoughts how we get from my sequence of we can even think about it, almost decreasing elements in U that bring us into partitions. So if we have the domain of F in the second characterization be an element of U instead of omega, is this equivalent? So yes. Yes, this is well, yeah, it's not going to really change anything if you replace it with any infinite set, right? So when we are looking at that function is arbitrary. Thank you. Okay, it's great when you give it a thought. I really appreciate that. So how can we build that partition, right? And we are looking at something that's almost contained. So that means in this sequence of neighborhoods. So it's only sticking out by finite piece, right? So we are looking at dual notions, really. So we are going to say that suppose that we do have a P point, which is the first definition. The other one is a claim. And suppose that we have an arbitrary function and I think it indeed is easier to make the translation via the partition. So omega is written as disjoint union of these PIs for the colors in omega. Okay, so now I know that, what do I know? So from being a P point, I would like to somehow say that the ultrafilter doesn't really see any piece of the partition, right? So there is two options. Either one piece of the partition is in U, and then we are done. There is nothing to do. So that would be where, of course, the function is very much related to the ultrafilter, and the other option is orthogonal to it. It has nothing to do with the ultrafilter because finite intersections are invisible, right? So suppose PI is not in the ultrafilter. So now what we want is that we want to build some sequence of neighborhoods of U such that when we get that pseudo intersection, it's going to do the job for the function. Are we closer to an idea now? Well, so I know that none of these things belongs to my, none of the PIs belong to my ultrafilter, which means that the complements do. Excellent, thank you. Exactly, right? So we have in particular that natural numbers without pi, right? They have to be inside of the ultrafilter. So now I get that there has to be a pseudo intersection. So let P satisfy that it is almost in and without pi. Well, that means that this P is going to stick out only by a finite piece in each of the pi's. And we are done. Excellent. Now it should be more or less obvious how to go in the other direction. Right, that is that if I do know that every function satisfies that. Exactly. Yes. So if if one of the pi's is in the ultrafilter, then this is being a constant. So now we want to go the other direction, right? So if I have a collection of sets, I want to find their pseudo intersection, right? So now from that collection, I want to cook up a function such that when I have a solution for that function, I get the pseudo intersection. Right, so I want to cook it up in a way, of course, that that function is not going to be now a constant on an element of the ultrafilter. Right, so I start with my collection, and I can look at well, the complements are not going to be quite a partition, but I can look at a 0, and I look at the complement of that. Well, now I would like to do something in a zeros. Right. So I have this piece. So I'm going to take for my first part n minus a0. And now I have my a1. So I'm going to take, again, without loss of generality thing, that a1 is almost included in a0. So I'm just going to take a0 minus a1. And so on. So I can take these guys. So this is going to be a partition. This is the same thing as having a function. And then, well, none of these can be in the ultrafilter, right? None of these pieces, because that's how I'm choosing. I'm looking at complements of the things that are in the ultrafilter. And now if I have any set that is going to intersect each of these pieces in a finite set, then when I look at it from the perspective of the A0s, then it means that it has to be almost included in all of them. Okay, so this was something to wake us up. And now I just wanted to give you a notion, stronger notion than that of a p-point, because there's a nice result for those. So if you require for every function to get either a constant map on a set in the ultrafilter, or instead of finite to 1, you are even more demanding and you want the map to be 1-to-1 on that set, then you get a notion of a selective ultrafilter. So this is a Ramsey theoretic property of the ultrafilter. Selective ultrafilters are, of course, p-points, which means that they are more difficult to get, right? Whenever you have a model of selective ultrafilter, then you also have a p-point in it, but you don't have to have it in the opposite direction. If you have p-points, then you do not have to have any selective ultrafilters. So now preimages of p-points are the ones that can be interesting. So there are some p-points that will have still infinite preimages, but there's this beautiful paper by Andreas Blas and Gugu Moche that says that these preimages can be finite, and actually they have examples of how large they can be exactly. So I just wanted to give one fun example because that one is easy to state without explaining too much. And that is when the ultrafilters on beta n are selective, then the preimage is going to consist only of 2 or 3 points. But of course, there is models of set theory where there are no p points, there are no selective ultrafilters, so it is consistent that all the preimages are infinite. But it is also consistent that some of the ultrafilters give quite a special behavior. I find it very entertaining, and we get that in the first result and in number of results in these papers. It's not that important that you're a p point yourself, but it's important that you're comparable to a p point, that you are above a p point in a certain order. So I wanted to mention this order. This is the Rudin-Kiesler order, because it is just a very, again, one of these notions in set theory that you see quite often. Moreover, there has been some very recent developments in relation to model theory as well. So you might have heard about Schillach, and he has worked a lot with Mariante Marialis. They proved one of the biggest open problems in small cardinals in set theory, but they are working in model theoretic terms, and they have been also looking a lot at this Rudin-Kiesler order on ultrafilters, often on uncountable set, and finding consequences about ultra products of some structures of a certain theory in model theory. So if you did go into the direction in your model theory part, which I'm not sure about, then there is some very interesting recent results. I think the paper first of these results started appearing in 2017, I believe. Okay, so let me just say what it is. It's very, very natural, but there is different ones as well. So there is the Rudin-Kiesler order, there is Blas-Kiesler, there is Katyetov order. So there are different orders, but there's Tukey order as well. They measure something a little different, all of them, but all of them are very natural. So the Rudin-Kiesler order says that U is dominated by V in this order if V is an image of U under some function. Okay, so there is a function from natural numbers to natural numbers such that if you look at its extension to beta n, then V is going to be mapped onto U. In some way, you can think that this ultrafilter V is at least as complicated as U. So that's sort of the idea that lies behind it, right? So when you have a P point below something, then that something is at least as complicated as a P point and carries over some of the properties, even though it doesn't have to be a P point itself. So it's obvious immediately that this is a partial order or partial pre-order, I would say. And you can of course take a quotient by isomorphism relation if you are Rudin-Kiesler related in both directions. And then from some perspective, it means that you are behaving in the same way. In particular, when you're looking at these pre-images, it is exactly the case that if you have isomorphic ones, then you will have the same amount of pre-images. Okay, so if you see this in the future, it won't be for the first time. And I just wanted to say something that's dear to me, that if you restrict yourself to just ultrafilters and minimal left ideals, that was already proved by Hindman, that the deeper images are going to be infinite. But we wanted to get a little bit more. So we tried to use one method first with p-points, but then we realized that you can have a model where every ultrafilter has a p-point rooting below, so you cannot rely on the non-existence of p-points in any argument. So we found a different argument that says that if we are restricting our attention from all of beta n cross n to just some minimum left ideal, we will still have a lot of pre-images, right? So let me just draw a picture here. I have my beta n and I take UV from some minimal left ideal. It can even be from two different ones. That's not very important. And I look at this pair and I'm interested in these pre-images, which I know there is infinitely many of them, but I don't know where they live. I do know because this pi does preserve the semi-group structure that we talked about. So if you look at the semi-group structure on n cross n and extend it to ultrafilters, and then the same thing just for n and ultrafilters there, then this pi is going to be a homomorphism. So, so that gives me that there is going to be some minimal element here that is going to be mapped there. But it could also happen that, for instance, you would be going across different minimal ideals, and you can also have elements that are not minimal that are being mapped in here, and that does happen. And this also happens. So what we contributed is that what also happens is this, that if you have any pair here in some minimal ideal here, then in the pre-image, you're going to have infinitely many pre-images in some minimal ideal of beta n cross n. So we were able to localize it a bit more. This is important in topological dynamics. So we didn't talk in that direction, but there is a natural motivation for that. So this is all that I prepared on slides. I'll give you a choice. Either you can go thinking about set theory and just enjoy yourself and celebrate the end of the course, or I can tell you something about stone duality. Everything that I talked about has an algebraic interpretation because there exists a correspondence, a perfect correspondence between compact zero-dimensional spaces, which are the ones that we talked about, and Boolean algebras, which are algebraic first-order objects. And the duality allows you to go from one world to another. So topological spaces are inherently second-order objects, whereas Boolean algebras are first-order objects. So the methods can be very different, but there is a two-way stream by stone duality to go from one to the other. And a lot of proofs in this area happen by doing that. So in the same proof, you start with a Boolean algebra, then you go into the space, you work with closed sets or open sets, and then you translate it back into a result about Boolean algebra, and maybe you come back again. So there's a lot of back and forth because it truly is a perfect duality. You can always translate it into just one language. And this is what I did here, that I did not mix the two things, but I think it's one of the very fundamental and beautiful results throughout mathematics. It appears not only in set theory, the topology, but the stone compact, the stone duality has many appearances in model theory, for instance. It gives you a relationship between the Boolean algebra formulas and types. So it's quite everywhere present and rediscovered. I've been to conferences where people were not aware of it and were rediscovering something that originated in 1936. Okay, so this is it for slides. So it's up to you if you want to learn about stone duality today. Some combinatorial characterization. Let me see the question. Oh, so yeah, so really the cardinality when it's infinite, it's always the same. It's 2 to the continuum because of compactness and being an H space. So it's either infinite and then it's huge and always the same, or it's finite. And then you have the direction that if it's finite, then there has to be a P point or a selective ultrafilter behind that, meaning it has to be root and Kiesler below. So you do have a direction that if it's finite, then it is because of existence of P points. And that means that you will have to be in a model where P points exist. I think that the paper says that, let me see, I don't remember exactly what the bounds are, but I think they say that the finite for images are between 2 and 9. So it's quite curious. Yeah. Yeah, there are different numbers, but I'm not sure if all of them can be attained. I know that you can attain 2 and 3, and I believe 5. I'm not sure. And you can you can get 2, 3, 5, 6, and 9. Very strange for set theory. Thank you for that question. Yeah, it's I think it's quite curious. Okay, so what about stone duality? Or any other questions, of course?
Yeah, can you talk a little bit about the stone duality?
Okay, well, I'll just respond here. Yes, thanks. Absolutely, it's
Just
my
a
most
briefly, perhaps, like give us an idea.
Yeah, it's my most favorite thing, as Jake and Elena would know. So I am. It's okay. We did this before. How did I edit the page last time? Oh, I think I didn't. I think I gave up and I opened a new document. Correct, right? So let's just do that. This way.
What program is this you are using?
Notability.
Notability.
It's it's on iPad. I have a student who is tech savvy, so I just learn from her. Oh, this just did something.
Okay.
Okay, yes. It's a nice app, but I'm sure that by now, okay, now it's decided that it's going to translate it into actual type letters. How do I get rid of it? Oh, I think I did. Okay. Sorry, I don't use iPad anymore. I have a sensitivity to screens, so I avoid devices as much as I can. But it's very useful for this. So stone duality is a two-way stream to go between the worlds of compact Hausdorff spaces that are zero-dimensional. Zero-dimensional means exactly that that the Klopen sets form a basis, and the mappings that we consider are the natural ones. These are the continuous maps. So this is category from the perspective of category theory, and we have a duality, which again is a notion that now exists in category theory. That just says that these two categories are really exactly the same. So Boolean algebras with homomorphisms. Is everybody familiar with what a Boolean algebra is? Okay, good. So one direction is very easy, and that is that if I do have a compact zero-dimensional Hausdorff space, then I can take the algebra of all Klopen sets, right? So if I have X in here, then Klopen X is a Boolean algebra. Well, it is Boolean algebra with respect to the natural operations, that is the union of two clopen sets is clopen, intersection is clopen, the complement is open, empty set is clopen, and the same thing for the space, right? So it becomes a Boolean algebra immediately. Now the other direction, and how do maps work? Let's just talk about it very briefly. So if I have a continuous map from X to Y, then I get my clopens here and clopens there. What is the natural clopen F? Where is it gonna go from and to, and what is it going to do? So continuous functions, right, are defined by preimages. So this is going to go in the opposite direction, right? Because we know that if I take an image of a clopen set in Y, preimage of a clopen set in Y, this is going to be clopen in X. I cannot go in the other direction because I don't know, right? It doesn't have to be open. And so here it goes by taking some C in here and looking at its preimage. So again, very simple. Now we want to go in the other direction. And we actually did most of the work already in the construction of beta, right? So let me give you an example here of beta, just so that we know how we go back. So if I have beta n here, well, what is the algebra of clopen sets of beta n? What are the clopen sets of beta n? Right?
Ultrafilters.
So that's the points of that, right? But now what are the neighborhoods of the ultrafilters? Those were these sets, right? All of these A bars, which were all ultrafilters that were contained in some A bar. So the clopen algebra is actually isomorphic to the power set algebra of natural numbers. And it turns out that we can go the other way. So, but power set of natural numbers seems a lot more feasible than the space of ultrafilters. But it's actually the other direction. That is that the stone space of this Boolean algebra, power set of n, this is our beta n. Right, so beta n, I can also define it by the property of extensions of functions without using ultrafilters at all. But it turns out that if I start with a Boolean algebra of power set of n and I take the stone space of that, then it is going to be homeomorphic to that, right? I just want to say that there is many ways to define that, and then we show that they're all homeomorphic. So I could have done it without any mention of ultrafilters and then show that the ultrafilters are going to work. So the stone functor works in the same way. So now instead of taking algebra of all power set algebra, I take any Boolean algebra A, and I'm going to assign to it a space called stone A, which is going to consist of all ultrafilters on A. Well, what are ultrafilters on a Boolean algebra? Very similar to what ultrafilters were on a set, right? I have that U is an ultrafilter if it's first of all filter. So again, the same notion. If whenever I have A that is smaller or equal than B, right? Boolean algebra gives me a natural partial order, and A is in my ultrafilter, then also B is going to be in the ultrafilter. So I'm closed under larger elements in the partial order. And if I have two elements that are in the ultrafilter, then their join is also going to be in the ultrafilter, right? So now I'm not using anything about sets. And then the ultra is going to say that if I have any A, then either A is in the ultrafilter or the complement of A, whatever the notation is going to be in the ultrafilter as well. So I have the same thing that I can do And it turns out that this is going to be a compact Hausdorff space. The way that you would verify that it's compact Hausdorff is the same way as we verified that beta n was. So there's really nothing more that you have to do as for methods. And now if I have any function, right? So this would be now a homomorphism from A to B, right? Then I can get a function that is again going to switch directions. So I'm going to get the Stone Age, and I'm going to look at where a certain ultrafilter goes. So look at the ultrafilter on B, right? Because that's what I'm going to look. So. And then I'm going to say what the age of that is. Well, I'm going to say that this is going to be, what do you think? So I'm looking for something that is going to be on A, right? So I'm going to look at all A in A so that the age of A is in my ultrafilter U. And I'm going to generate an ultrafilter out of that. Okay, so this is going to work. This is going to be continuous map. And as you see, it's a contravariant functor, right? I'm flipping the arrow each time of the morphisms as they go. But then if I compose two ways, I get the arrows in the correct way. So what the duality says, not only that I can take this representation, but that if I start with a compact space X, I take the algebra of Klopen sets, and then I take the space of ultrafilters on this algebra, I get a space that's homeomorphic to it. So I get that for every X, this is going to be homeomorphic to the space of ultrafilters on its Klopen algebra. And similarly, if I start with any algebra, then this is going to be isomorphic as a Boolean algebra to the Klopen algebra of its Stone space. Right? So in particular, it's a representation theorem. It says that every Boolean algebra is actually a set algebra. It is the algebra of sets, of Klopen subsets of some Stone space. Let me just recall that if I have a finite Boolean algebra, right? And this is something that usually people see in undergrad. That means that A is actually the full algebra, power set algebra for some finite set. And that's still in correspondence because there is only, compact spaces among, finite spaces are going to be discrete compact Hausdorff spaces. Therefore the algebra of Klopen sets is all of the subsets. Now, if A is infinite, then we have more algebras than just power set algebras, right? Power set algebras correspond exactly to the Chicstone compactifications of discrete spaces. But still I have that A is a subalgebra of some power set algebra, namely it is some algebra of Klopens of some space X. Well, I guess X I used for a set here now, so let's use this Stone A for, right? So it's really that Boolean algebras do come from sets in this meaning. And let me maybe give some examples that would be different than just beta n. Well, not to go too far, if I look at the Chicstone remainder, right, n star that we talked about today over and over again, these are the non-principal ultrafilters. That means that we are forgetting about finite sets. And on the side of the Boolean algebra, this is taking the power set of natural numbers, and I'm taking quotient by the ideal of finite sets, right? So that that is an equivalence relation, right? It gives me an equivalence relation on sets. So it's easy to describe that, this is going to consist of all equivalence classes of subsets of n with respect to that equivalence of almost equality. Right, so I will have that two sets are equivalent if and only if they are almost equal. So, in n star, that makes no difference. In particular, all finite sets are going to be equivalent to the empty set, right? So finite sets, that's the ideal, that in the quotient becomes the new zero, right? And every element is, look at your element of the Boolean algebra, modulo something in the ideal, right? You can add that ideal to it. So now I get that n star is the stone space of this Boolean algebra, and I can treat n star totally Boolean algebraically, and that has been done a lot. That's on daily basis. The same thing for omega 1 star. This is power set of omega 1 modulo the ideal of finite sets. So now Katowice problem is about whether there exists an isomorphism between these two Boolean algebras. And these are all very large spaces. So just to give you something smaller, another very zero-dimensional space that is not trivial or not finite would be the Cantor space, right? The Cantor space is zero-dimensional, it's metrizable, and people are not afraid of it. And the Boolean algebra of Clopens has a beautiful algebraic characterization. Well, it has to be countable because this space is metrizable. It doesn't have any atoms. What that means is that whenever I have an element that is not zero, then there is something below. There is nothing that is immediately above zero. And if I have a Clopens set in 2 to the z, well, it can never be just a singleton because it's a perfect space. So I can split it into two Clopens sets. So I will never get an atom, right? So it is atomless. And it turns out that there is only one countable atomless Boolean algebra. So that corresponds to the Cantor space being the only metrizable zero-dimensional space without isolated points. So you have immediate translation between these topological and algebraic concepts, and sometimes it's just so much easier to see something algebraically than topologically and vice versa, that it's just super, super useful. Then we can, of course, have larger Cantor cubes, right? And it turns out that there is another way to uniquely describe what this algebra is, and that is that it is a free algebra on Aleph not many generators, right? So you take Aleph not many things and you independently generate. So in any sense, like free group, right, that you generate by free words, this is the same concept, just with the operations of Boolean algebras. So if you have kappa here, then this is, of course, excuse me, free group on kappa many generators. Okay. And then let me maybe mention this thing that we talked about today. We had the notion of an extremely disconnected space, which was really only applied to beta n and beta n squared. But it turns out that if I have an extremely disconnected space, that corresponds to the Boolean algebra being complete. That means that whenever I have any subcollection, so which can be infinite, then there exists a join of that or a meet of that, right? So I can have now infinite joins and infinite meets, which sort of leads to a whole special theory, because there is a lot of results about complete Boolean algebras that are not true when you take away the completeness. But again, those spaces that set theorists like, they are extremely disconnected. So it's worthwhile to restrict your attention just to that algebra, just to this category. And again, here it's the stone duality just works perfectly. Sometimes you have a well-defined subcategory, but the other side is not going to be as nice. And this is, for instance, example of sigma complete Boolean algebras. So complete means that it's really complete. That means that you can take as many elements as you want. Sigma would be complete with respect to countable subfamilies. So for instance, the Borel algebra, right, on reals or on a Baire space is going to be sigma complete, but there is no nice description of how the stone space looks like. So the stone space is the space of ultrafilters on this algebra, and that's about it as for niceness of, so some things are not as topological, the things in algebra, and vice versa, right? So some properties just really make sense, more sense on one side than on the other side. So yeah, this is fascinating. And one thing is that maybe you would like to get rid of the zero dimensionality, right? Because it seems somewhat special. A lot of spaces are connected, all the manifolds, right? And spheres and so right. But there's two things. One thing is that you can always cover any space by a zero dimensional space in somewhat irreducible way. So somehow you can approximate it by zero dimensional space. And another thing is that you do have versions of that for things that are potentially connected, but you do not have a duality, a perfect duality. So you could get maybe a lot of algebraic objects corresponding to the same thing. Let me just mention that because this is also something that can be combined with model theory and set theory in a productive way. It's called Wallmann's compactification. If these dualities is something that interests you, because it connects different worlds, so you can have just compact spaces and bounded distributive lattices. Right, so just bounded means that they have the greatest and smallest element, which again, when you start with a compact space, what you do is that you adjoin to that the lattice of all closed subsets. So often in topology, the space of all closed subsets is denoted by 2 to the x, which of course is not what we would expect elsewhere. If with the lack of topology, these would be all subsets of x, but in topology, these are all closed subsets of x. In other notation, it's sometimes x, like an exponential, it's the hyperspace as well, it's another way. But here it's as an algebraic object, this is a lattice, but it's not necessarily Boolean algebra, because if you have a closed subset in a connected space, then its complement is not going to be closed, because otherwise they would be clopen and your space was not connected to start with, right? So you don't get, it's not complemented. If it was complemented, then it would be a Boolean algebra. So now you can take an arbitrary lattice and you can look at, well, arbitrary distributive bounded lattice, makes sense. And then you can look at the space of all ultrafilters and you equip it with topology of closed sets, now the ultrafilters that contain a certain element. And that's going to work well. The thing is that here, if you start with X, then you have many lattices that are going to correspond it in a way that if you take any basis for closed sets, that is, say, closed under finite intersections and finite unions so that it forms a lattice, right? That forms a lattice. Is going to return back as a space of ultrafilters X. So it's not one-to-one anymore. It's not that if I have two different Boolean algebras, I'm going to get two different spaces. Here I could have, uncountably many closed sets, but I have a countable basis, so I get definitely lattices that are not isomorphic, but their Wollman representations in spaces may be the same. However, it's still something that can be very useful because you can talk about properties of the space, and for example, connectedness is such in terms of formulas on the lattice, right? So there is a formula that tells you that if it's satisfied about a lattice, that tells you that the ultrafilter space is connected, and other properties, right? So you can use the algebraic structure to express things about a lattice, and then you can use things like elementary submodels of set theory and take intersections to get some reflections of properties of spaces. So it gives you a big variability, being able to work in between the topological and algebraic world. Anyway, so this is, if you have any questions about it, I'm very happy to answer. I hope it made some sense.
Any question for Dana? Yes. Yeah. So I think that is the end of the lecture, and also the for the program. I just want to thank Dana and also all the other lecturers for giving these lectures, and also thanks to the participants for participating. And yes, so I'm happy that Yen King he expressed that he has learned a lot, not being in set theory or a logic background. So that pretty much achieves the goal of this program. So hope that in the future there will be more people who will benefit from it. And also, the recordings and the notes will be available. And I hope that whoever you want to share it with, feel free to share the resource that is available. And yeah, so once again, thank you, Dana. So hopefully we'll be able to meet after the pandemic has died down, and we'll be able to hopefully work out some programs together.
Most definitely, it would be a lot more pleasurable if I was actually there.
Yeah, that's true. Yeah.
And also the interactions, right? One thing is that I can speak for a couple of hours, but if we could actually have a discussion, then that is another level. And usually the discussions are the most productive part, but this is definitely great that it exists and you are able to do something low cost as well to start, right? It's I think this is fantastic.
Yep, that's true.
Yeah. And yep. I hope that not that the participants learned, but they will want to learn more.
Yep, it's very true. Hopefully people will benefit from this and will actually go a level higher. Yeah.
That's right, to build a community.
Yes, right. So thank you, everyone. That's it for the course, and see you again. Okay.
Thank you.
Bye.
Have a good day. Bye.
Yeah, you all too.